Okay, so let's start. So this is the website to our tutorial. So we have just uploaded the slides for the first half by Professor Matthew Gambale. So if you click the link, you can download the slides as a PDF. And for the next part, I'll be giving a coding tutorial on how to write code for running graph neural networks, and especially take a look at the sketching architecture we introduced. And I have provided the Jupyter notebook hosted on my GitHub repo, so you can download from this link. Alternatively, you can open it in Google Colab. For this tutorial, I'll be testing the code in the Google Colab for demonstration purpose. So, okay, so let's get started. So this notebook serves as a coding session of this AAMAS tutorial on graph neural networks, learning representations of robot team coordination problems. And this tutorial divided into two parts. The first part will introduce you to some basics of how to write code on heterogeneous graph neural networks using a deep graph library. And the second part will showcase how to solve a multi-robot coordination problem with SketchNet, and also show you how to train a SketchNet with the imitation learning using the code base. Due to time limit, we won't be able to actually train a model, so we will show the training code and provide a training checkpoint so you can test with it. So first thing first, the environment setup. So for basic setup, to enable the CUDA availability, you need to check the edit and go to the notebook setting to see if you have CUDA enabled. So by default, Google Colab will run only on CPU. So if you want to use GPU, just select GPU here and click Save. Then you can use this command to check the CUDA version of the Google Colab runtime you're connected to. So in this case, we are using CUDA version 11.1, and the Python version is 3.7. And for this tutorial, we'll be working with PyTorch. So first, we need to import the packages from Google Colab. And after this, you can run the next code to check the version of the torch and also to check if the CUDA is enabled. And if you get true, it means CUDA is enabled for this runtime. And you can see there's one GPU returned by the CUDA device count. Alternatively, you can check the current device and also check the device name to print out the device name. In this case, we're running on a Tesla K80 from Google. And apart from that, the other things you need to install the deep graph library, which is not provided in the Colab runtime. So for that, you need to so here I give a link to the install page. If you click the page, you'll go to the installation page and to select the correct command. For this case, we're selecting CUDA version 11.3 because our torch version is with CUDA 11.3. So because our DGL is using PyTorch as backend, so they should match each other on the CUDA version. So we select CUDA version 11.3, and we're using a pip install for runtime, and it's Linux, and the Python is 3.7. So this gives us this command. So we just copy paste this command here to the first part, and just we can hit it to run to install the DGL library on the Google Colab. Alternatively, if you don't need GPUs in your local, or you only want to work with CPU version, you can select none here, which will give you the command to install CPU only version. So here I'm also included the command to install the CPU only version here. And once you have the package installed, you can verify the installation by check the import and print out the DGL version. So by default, when no backend is selected, DGL will try to choose a backend automatically. So in this, DGL supports PyTorch, MXNext, and TensorFlow as backends, and it will choose them using the following rules. So first, there's a DGL backend environment variable, which you can use it to specify whether you want to use PyTorch or TensorFlow as backend. And also, you can also modify the JSON file under this folder. And for this tutorial, we'll be using PyTorch as backend. That's because we have imported PyTorch before DGL, so DGL automatically pick PyTorch in our case. And before we going deeper into actual codes, let's just do a recap of some basic definitions of graphs. So graphs express nodes and edges as entities and relationships, and both can be typed. In case in e-commerce, we can have user nodes and item nodes, which can be two different types of nodes. And in DGL specifically, it has a graph-centric programming abstraction with its core data structure, DGL graph. DGL graph provides its interface to handling a graph structure, its node edge features, and how the communication can be performed using those components. To give you a basic definition, a graph is a structure with a set of nodes as V and a set of edges. And an edge connects a pair of nodes. U and V indicate that there's a relation between them. So this relation can be either undirected or directed. For example, if you have a social network and you want edge to represent the friendship, which is mutual. So in this case, edge is undirected. However, if you are dealing with a follower graph in Twitter, then the edges are directed, meaning person A is following person B. And also the graph can be weighted or unweighted. In a weighted graph, each edge can be associated with a scalar weight, like in the STN, where the weight is just the temporal constraints, or a high dimensional weight feature. And like we said before, the graph can be either homogeneous or heterogeneous. In a homogeneous graph, all the nodes represent instances of the same type, and all the edges represent relationships of the same type too. For instance, a network of homogeneous robots is a graph consisting of robots and their connections representing the same type. And on the other hand, in a heterogeneous graph, nodes and edges can be of different types. For instance, if we have a graph encoding representing a marketplace, we'll likely have buyer nodes, seller nodes, and product nodes that are connected with. A buyer wants to buy some products, or a buyer has bought some product, and a buyer is a consumer of a seller, or a seller is selling some products. So like those edges have different meanings, so it's better to formulate them as different type of edges. And specific to bipartite graph is a special commonly used type of heterogeneous graph where there's only exist edge between one type of nodes to another type of nodes. For example, in a recommender system, one can use a bipartite graph to represent the interactions between users and items. And in DGL, it represents each node by unique ID, which is the node ID, and each edge by another unique ID, edge ID. And an edge can be associated with with two numbers. The first number can be the ID of the source node. The second number is the ID of the destination node. So once you know that the numbering of node and edges starts from 0, and all the edges are directed in DGL. So basically, if you have undirected graph, you need to convert it to a direct graph by allowing the edges to flow from both sides. And if you want to specify multiple nodes, DGL takes a 1D integer tensor, like it's basically a list of node IDs, which is called node tensors. And to specify multiple edges, it uses a tuple of the node tensor, U and V, where the UI and VI decides an edge from UI to VI. And in this case, such case, we have the one way to create a graph instance is to use DGL graph method, which takes input this all the edges in the graph. So here we have a simple example of a homogeneous graph which only has four nodes and 4 edges. So to create a graph like this, you just to specify the node tensors, the 2 node tensors. The first one is the IDs of the source node of every edge. For example, for this case, you have 3 edges coming from node 0. So the source node of the first 3 edges is 0. And the destination node ID of the first 3 edges will be 1, 2, and 3. And then you have the first edge, which is going from node 1 to node 3. Here you have 1 and you have 3. And you can use this edge information, can pass to the graph function to build the graph. If you hand over this functions, it gives you a descriptions of the parameters of these functions in DJL. And you can either use source code with GitHub source or open in another tab. For this case, if you run this code, it will build a graph with 4 nodes because in this case, the largest ID of the node is 3. So which in this case means you have 4 nodes. That's why the number of nodes are as inferred from the max node ID in the given edges. And you can access nodes by calling the graph.node API and also check the edges with the edge API. And if you want to print the full information of each edge, including the start, the ID of its source node, the ID of its destination node, and also the edge ID, you can pass this form equals full. So those are the printed output. The first one is this is the IDs of the node, and this is the IDs of the edges of the source node and the destination node, and also the ID of the edge, which starts from 0. So alternatively, if the node with the largest ID is isolated, meaning there's no edges coming from the largest node, you can manually specify the number of nodes when you're building the graph. So for this case, we pass this variable, number of nodes equals 8. Even though in the edge tensor, we only specify the largest node that is 3. If you run this code, you are still building a graph with number of nodes of 8. Next, we'll show you how to visualize a graph. When visualizing a homogeneous graph, we can first convert it to a network X instance. So network S is a Python package for creation, manipulation, and study for structured, and it's extremely useful for a graph-based data. So like it's not a deep learning library, so you cannot train graph networks on it, but it provides some classic algorithm for graph preprocessing. And let's go back to the tutorial. So for this case, Deep Graph library provides this two-network API to convert a DJL graph instance to a network X instance, and then you can plot it using a matplot. So here, if you plot this SG2, which is created by specifying the number of nodes, you can see that in this graph you have all the 8 nodes it's present, even though there's only edges between those 3 nodes, those 4 nodes associating with this graph. And if you can also print the first graph we created, which is only has this 4 nodes. And when plotting the graph, because a graph structure is flexible and you vary the nodes, the position of the node, so you need to pass this this position variable. It generates a random positioning for each node in the graph. You can either use a command layout, which usually gives you a good looking graph. Alternatively, you can use this. You can give a circular layout, which looks like a circle. This is what we use for when plotting the graphs used by SketchNet, because it gives more clear illustration. Alternatively, you can also do a random layout. And alternatively, you can also add the following code to also like draw the labels of each edge. So in this case, if you run this code, it will also show the IDs of each edge between from 0 to 1, node 1, node 2, node 3. So like those are different algorithms you can test when like visualizing a graph. And next, we'll talk about how node feature and edge features are stored in a DGL graph instance. So first, the node and edges of a graph can have several user-defined named features for storing graph-specific properties of node and edges. Those features can be accessed with the N data, which is node data, and edge data, which is E data, those two interface. So for this instance, we are creating a graph which has 7 nodes and 4 edges. And we use the following code to create a node feature named X, which is a 2-dimensional feature, and also a edge feature named W, which is scalar integer. And you can see that when you directly create a graph, the node data and edge data is blank, it's empty, because you don't assign any feature to them. And after this feature assignment, when you print out the graph, you can see that the node data and edge data, each a dictionary, and the key is a feature of the node. For instance, after you do the assignment, the key X appears in the node data with the data we just assigned so far. And you can get the first node, you can get node 1's feature X by first passing the key of the feature name, which is X, and then the ID of the node ID, which is 1. And you can also do so for multiple nodes or access the features of multiple edges. For edge data, you just change the N data to E data and then pass the name of the feature with W, and also the list of edge IDs you want to access. In this case, is the first edge and the first edge, which has 3. And note that a node can have several user-defined named features, meaning you can also assign a different tensor to be the feature of the node features under a different name. So in this case, we are adding a node feature named Y, which has a different dimension, which is a 5-dimensional tensor, 5-dimensional feature, which is different from this 2. So to assess this, you just change the names to Y, and then you can print out. Also, you can have different names for you can use the same names for the features for node and edges, and they're different because they are stored. So for here, you can have a node feature that also has the feature name is W, which is the same as the edge feature. But because this time it was stored in a node feature, so it doesn't interfere with what you're putting in the edge data. And it can be of different dimension as well. And here are some important facts about the node data and edge data interface. So only features for numeric types can be allowed. It can be scalars or vectors or multidimensional tensors. And each node feature has a unique name and each edge feature has a unique name. But the same name can be used for both node feature and edge feature to different ones. And a feature is created with tensor assignment, like those lines, which assigns a feature to each node type in the graph. And the leading dimension of that tensor must be equal to the number of edges and nodes in the graph. So you cannot assign a feature to a subset of nodes in the graph. And feature of the same name under the same node edge type must have the same dimensionality and data type. And the feature tensor is in row major layout, meaning like each row slice stores a feature of one node or edge. And then let's go to the heterogeneous graph part. So a heterogeneous graph can have different type of nodes and edges. And in the DGL implementation, nodes edges of different type has independent ID space and features to storage. For example, in the figure below, the user and game nodes, the user node and game nodes has separate storage for their IDs, and they can have different features. Like both IDs start from 0, but they are keyed by different names. And creating a heterogeneous graph is straightforward by specifying a series of type of edges, one per relationship. So for a heterogeneous graph, we use this DGL heterogeneous graph interface to create one, and it takes into a graph data. So here, the graph data is a dictionary keyed by a string triplet, which identify the type of the source node, type of the edge, and the type of destination node. And then the information should the list the tensor nodes of the source node IDs for each edge and the destination node IDs for each edge. For instance, in this graph, we're creating a graph of 3 type of nodes, which is robot, task, and location. And 4 type of edges. The first type is edges where semi-robots can communicate with robots. So for this type, we are parsing a fully connected graph, a dense graph. So basically, every robot is connected to another robot. So in this case, the robot 0 is connected to both 1 and 2, and the robot 1 is connected to both 0 and 2. And also the robot 2 is connected to 0 and 1. So in this case, the communication graph is a dense graph. So if you prefer only let some of the robots communicate to some of the other robots, you can change this data to just manually specify the direction of the communication. And we also have an edges representing a robot is executing a task. In this case, we have robot 0 executing task 2 and robot 1 executing task 3. And we also have this task in locations to represent the location constraints of each task, in which case we have 2 locations, whether it's 0 and 1. And last, we have the locations near locations, specifying that the 2 locations have some is near each other. And once you create such graph, if you print out the graph, it will tell you the number of nodes. In this case, we have 2 locations, 3 robots, and 4 tasks, and number of edges for each type, and also the meta graph. We'll talk about the meta graph later during the graph visualization. But let's first go over some basic properties of this graph we just created. So you can access the node types using the node types parameter and variables and edge types, and you can use this canonical edge types to print the full edge names. So basically, the node types we have location, robot, and task. This is sorted by alphabet. Edge types we have near, communicates, executes, and in. So if you want to do the pole edge types, the canonical edge type will give you this full name from the source, edge, and destination for all the 4 types. And note that a homogeneous graph or bipartite graph can be considered the special case of heterogeneous graph. It's only 1 type of edge. So in this case, we build a homogeneous graph for location graph, where we only have location nodes, and their relationship can be the edge type is near. And or we can do a bipartite graph between the robot and task. So in this case, there will be only edges coming from robot to task, and we don't have the robot communicate with robot graph. And for visualizing a heterogeneous graph, it's a bit different from a homogeneous graph, because for a heterogeneous graph, we often use this meta graph for visualization, which is called the schema of the graph. It specifies the type of constraints on the set of nodes and edges between the nodes. So a node in a meta graph corresponding to a node type in the associated heterograph, and an edge UV in a meta graph indicates that there are edge types from the node type U to the node type V. So you can code this function to check the edges of the meta graph. In this case, because we have 4 types of edges, in the heterogeneous graph. So the meta graph will give you four edges, each associated with one edge type in the associated heterograph. We have location to location, robot to robot, and robot to task, and task to location. And to plot the meta graph, we can use a graph visualization package, which is already installed by the Colab. But if we want to call it in Python, we need to install the PyGraphViz package, which we can install by running this command. It will take a couple of seconds. So once it's installed, we can visualize the meta graph by here I wrote this simple helper function to save the meta graph in the local server using and open it with OpenCV. So if you run this code, you will generate a you can refresh the file section in the Colab, and you can have a base graph, which you can directly open here and also showing it here. So basically, you are for this. The meta graph will be, we have robots communicate with robots, and robots execute tasks, and the task was in different locations, and we have locations near each other. And we can also visualize the graph instance. For that, we need to first convert it to a homogeneous graph. We'll talk more about converting a heterogeneous graph to a homogeneous graph later, but for current session, we just need to know, we need first to call this to homogeneous function to convert a homogeneous graph representation of the heterogeneous graph, while only preserving the type information and discarding the features. And then we convert to a network X. And then we can use the following code to by the layout. And then for this code, we are assigning a different color for different type of nodes from the original heterograph, and we can draw it here. So for instance, this is the graph we just created with the with this code. And if you check, we have two locations, which is 0 and 1, which colored inside. And we have 3 robots. They are communicating with each other. So you can see there's arrows between all of them. So we have 3 robots. And we also have 4 tasks. And those 2 edges tells you that which robot is executing which task. And those edges from the task to location, depending on like those 2 tasks will happen in location 0. So they cannot happen at the same time, because the location constraints. And more information about working with multiple types. So for heterogeneous graph, when multiple node and edge types introduced, users need to specify the specific node and edge type when invoking a DGL graph API for type-specific information. In addition, node and edges of different types have separate IDs. So if you just directly call this number of nodes, it will give you all the nodes, like the 9 number of, for this case, is 9. And if you want to know the number of nodes for a specific type, for example, we want to learn how many task nodes in this graph, we just pass the name of the node, and to give you 4. And because nodes of different types have separate IDs, so if you just direct code the node API, this will not work. This will give an error because it's ambiguous and DGL doesn't know which type of node you want to access. So instead, you should use the following code, which, for example, pass the code names. For example, if you want to do access all the robot nodes, you need to pass the string robot as a node name, and then you get the IDs of the robot nodes. And setting And getting features for a heterogeneous graph is similar to a homogeneous graph, except you need to specify the node type or the edge type first before accessing the feature named features. For example, here we are assigning a tensor shape of shapes 3x1 to the robot nodes under the name HV. And here we are assigning a random integer from 1 to 10 to this edges XQs under the name HE. So this can be the width of the edge type robot XQs task can be seen as the time that takes for robot to execute a task. And particularly if the graph has only one type of node or edge, then there's no need to specify the node or edge type because there's no ambiguity in such cases. So for example, if you have this robot graph which only have robot communicates with the robot near the robot. So in this case, we only have one type of nodes, which is robot. Although we have two types of edges, one is communication, another one is location, and that's spatial. And in that case, we don't need to specify the nodes like the robot because there's only one type of node. So when you check the node data, the DJI API nodes you want to access the features of the robot nodes. And in that case, there won't be any errors for doing so. And also when the edge type uniquely determines the type of source and destination node, one can just use one string instead of a string triplet to specify the edge type. So for this graph, you can use communicates to identify the first graph without showing the full names robot communicates with robots because the edge names are unique from each other. But when you have two different edges share the same name, like you can have robot near the robot, and also you can have location near the location. In that case, if you not associate one of the edge types, you need to pass the full triplet because in that case, a near can have two meanings, whether it's a robot near robot or location near location. So one can also create a subgraph of heterogeneous graph by specifying the range shapes you want to retain with features copied if any. So in this example code, we first build a graph with 4 edge types, and we associate the features to the robot node under the name HV. So we can call in this function edge type subgraph to only extract a graph that contains the robot part, where there's 2 edge, only preserve the robot communicates robot and robot executes task where ignoring the location part. And in that case, in the subgraph, the robot feature is copied. So you can set the shift features will be copied as well because it's present in the subgraph. And more on converting a heterogeneous graph to a homogeneous graph. A heterogeneous graph provides a clean interface for managing nodes and edges of different types and their associated features. This is very useful when the features of node and edges of different types have different sizes and you want to apply different operations on them. And if the above condition do not hold and you don't want discrete node types in the modeling, then you can convert a heterogeneous graph to a homogeneous graph with this to homogeneous graph function. And what this function does is it relabels all the nodes and edges of all types using consecutive integers starting from 0. And it will merge the features across the node types specified by the user. So if you don't specify anything, it will just create a new graph but doesn't do anything with the feature. So the feature of the previous graph is not preserved. So in this case, if you create a homogeneous graph of the robot case, and in the following 4 lines, we associate different features to the robot node, task node, and the communication edge, execute edge. And by default, if we convert to a homogeneous graph, those features are not merged, so meaning they are not present in the homogeneous graph. So if you check if in the node data they have the name HV, it gives you false. And but you can copy the node data and edge data specifically by passing this parameters when doing the conversion. But however, you have to remember that when merging the features of different types, they have to be in the same feature dimension. So in this case, even though both communicates and executes has a named feature HE, they are of different shape. The first one is 1 dimension, the second one is 2 dimensions. So if you try to merge them to form the homogeneous graph, they will give an error and says that cannot concatenate the columns HE for both types. For the following code, because the node data are both node features are 1-dimensional, so they can be merged together. So you can just pass them to merge the node features, which gives the concatenated graph, which is 7×1 tensor. And specifically, the original node types and type-specific IDs are stored in homogeneous graph as at the features. So for example, for here, you can see that in this case, if you print out the node features, like the node type information became the features in the homogeneous graph. So in this case, the first 3 nodes in the homogeneous graph respond to the robot feature at the robot node, and last 4 respond to the task node, and they have this, and the previous IDs stored at this NID feature. And the same thing happens for the edges. So basically, the 2 edges assign different feature IDs for communicate and execute, and they have different IDs stored as features. And for modeling purpose, one may want to group some relations together and apply the same operations on them. To address this need, we can first take an edge type subgraph of the heterogeneous graph and convert the subgraph to a homogeneous graph. So the following code will extract the robot part of the heterogeneous graph and convert to a homogeneous graph for computation purpose. And next, we'll show the core part for writing a message passing code for both homogeneous graphs and also heterogeneous graph neural networks. So we have shown this before in the first section, which basically the message passing paradigm defined the following edge-wise and node-wise computations for the next step or next layer. So here we have the message function, which is defined for each edge type to generate the message by combining the edge features with the features of its source node, either source node or destination or both. And the update function is defined on each type of nodes to update the node features by aggregating its coming messages with different polling operations or attention mechanisms. And that was produced by the reduce function. So I'll explain all 3 functions in the following steps. Let's first go to the message function. So the message function takes argument edges, which is a batch of edges generated by the DGL API to internally represent a batch of edges. It has 3 members: the source, destination, and data to access the features of the source node, destination node, and edges. So for example, this code defines a simple message function, which returns the summation of the features from its destination. Here we use HU and HV here. So it will sum the HU feature from the source node and HV feature from its destination node and save the computation node at M. At M field, and then send it to the destination node's mailbox. So basically this code, because this message function is very simple, so the DGL has some built-in functions specific for that to simplify the code development effort. So basically this function is equivalent to this following built-in functions. Basically you add the feature from the U and the feature from V to create new features on the edge and send them to the during the message passing. And the reduce function takes a single argument nodes because it's applied on each node types. So this node argument, it's a batch of nodes, and it has members mailbox. So mailbox is a very important notion in DGL that stores all the messages you received from your neighbors after the message passing. And some of the most common reduce functions are the sum, min, max, and minimization. It's different ways of how you aggregate information. So for this case, this reduce function just do a sum over all the messages over the message dimension and return it as age. So this one is equivalent to this sum built-in functions. You can run both code to show to print out the function that was like the built-in message function. This will be the simple reduce function, just to sum over all the received message without further preprocessing it. And then we have this update function takes a single argument node as described above, and this function operates on the aggregation result from the reduce function. It will combine it with the node's original features at the last step and saving the results as node features. So like we said, DGL has implemented some commonly used message function and reduce functions and built in the namespace function. So in general, it is suggested if the message function to use the built-in function whenever possible, since they are heavily optimized and automatically handle the dimension broadcasting. And the list of supported built-in functions can be found in this link. So in its documentation, we have a list of different built-in functions. The naming of the built-in functions just directly tells you what this function did. For instance, for this binary message function, the first one, this one just add a feature from from the source node and destination node. For this one, just subtract a feature from source node to the destination node, and this one just multiply two features from the source and destination. So it is also possible to invoke only edgewise computations by using this apply edge function without invoking message passing. This often serves as a pre-processing step on the edge features, which we will show it's an important step for graph attention networks. It takes the edge. It takes a message function with parameter by default and updates the features of all edges. For example, for this one, when you call this apply edge, it will add the EL features from the source node and ER feature from the destination node and store the result as E in the message. So here is actually E left and E right. So for message passing, the most important function is this update all function, which is high-level API that merges message generation, message aggregation, and node update in a single call, which leaves the room for optimization as a whole for the internal DGL API. The parameters for this update all function are a message function, a reduce function, and update function. So one can also call the update function outside the update all and not specify it in invoking this function. And this is recommended behavior because in this case, because the update function can usually be written as pure tensor operations to make the code concise. So for instance, for this code will generate the message M. So we can first go to the update all function. We pass first, we use the built-in message function, and second is the built-in reduce function. So what the message function does is in this naming, so it generates the message M by multiplying the source node U, the feature of the source node under the name FT, and the edge features under A, and then send them to the destination node. And then the reduce function will take this message under the name M and do a summation over all the received message to store it as the FT in the output. And after doing this message function and reduce function, we update the features by multiple of the feature with 10 and return it as a final feature output. And this example is equivalent to this following equations for manipulating the producing the output features from the input feature and edge feature. So in practice, we'll have more customized message functions and reduce function for SketchNet because we have different type of nodes and we have edge widths and also various attention mechanism. But the basic idea will be the same. Basically, we will specify the message function and the reduce function and call this update all to update to perform the computation and then do a reduce update from outside for further like tensor operations on the features before we outputting them as a final feature. So the message passing on heterogeneous graph, it's no different from homogeneous graph. Basically, it can be split into two parts. The first part, we do message computation and aggregation for each type of edge, like each relation. And then we have an extra reduced step that merges all the aggregation results from all edge types to compute the output for each node type. So in this case, the interface for invoking message passing on heterogeneous graph is a multi-update all. It's like a update version of the update all. Like update all only handles one type of edges. And here, the multi-update all will handle the message passing for all type of edges. Therefore, instead of taking one message function and one reduce function, it takes a dictionary containing the parameters of this update all, but within each relationship using the edge type as a key. And also we have this actual reduction step that represents a cross-type reducer. This reducer can be either a summation or taking the minimum over all the features or maximum or just mean or just simply stack them together, like stack the features from different edges. And here we'll take the robot graph we built as an example. So we initialize the graph data, we specify the edges. Here is the full communication graph. So every robot is connected with every robot to let communication flow between them. And for heterogeneous graph, when this part code generates some node features, for generating node features, for running a heterogeneous graph, we need to specify the input dimension and output dimension of each node type. So for this case, we are assuming that the robot feature will have one dimension, the task has 3 dimensions, the location will be 2 dimensions. And we use this parameter for output. And then the input feature is organized as a feature dictionary keyed by the name. So for this case, we need to provide features for the robot node and also for the task node and also for the location nodes. And after running this, you will check we have, if we print out the feature dictionary, it's a dictionary of keyed by the robot nodes as 3, the feature is 3x1, and for task node, it's 4x3, and the location node is just 2x2. So here we're using some dummy data just for demonstration purpose, but in practice, those features will be generated based on the state of the problem. Like in SketchNet, we prepare the input feature based on the current partial schedule we have constructed so far. And for graph, heterogeneous graph neural network, we are assigning, here we construct learnable weights for each type of relationship. So for this case, for each type of edge in the graph, we use a assign a linear weights that transforms the input dimension of the source node to be the output dimension of destination node. So for this case, this gives us a module dictionary in PyTorch, which has 4 different linear layers. The first one is for the edge type near, which the input feature is 2. Because location near location, the location is 2, and output feature is output feature of location, which is 4. And for the executes, the input feature will be the feature of the robot, which is 1, and the out feature will be the out feature of task, which is 8. So here we are enabling the bias for every linear layer, but it can disable it by passing bias equals false in this when building this linear layer. And then we need to provide a message passing dictionary, which is basically a dictionary of functions. So for this code, we are preparing this function dictionary for every type of edges in the graph. So basically, we unpack the source type name, edge name, and destination node name, and then first we transform the source node. We transform the feature of the source node using this learnable ways to make it match the output dimension of the destination node. And we save it on the graph for message passing. And this line of code will specify the per edge type message passing functions. For this case, it just simply we copy the features from the source node and send it to the destination and store it in the M. And in the destination node, we just compute the mean of all the messages. Note that the result is saved to the same destination feature H, which hints a type-wise reducer for aggregation. So because even though they are saved as the same destination feature H because they are coming from different edges, the DGL knows how to do them separately. So this code gives you a feature dictionary that keyed by, so there's a message function, reduce function for each type of edge, for near, communicates, execute, and in. And the rest part will be simple. We just use this multi-update all function, passing this function dictionary and specify the actual reduce function for the final output. And if you run this, it will trigger the message pass and do the computations internally. As a result, you will, because here we are using this H, so basically the computation output will be stored on each node type on the data, on the feature name H. And in this case, those are computation results. So note that for the task node output features, for the first 2 tasks, the features are 0. This is because if you go back to the graph visualization part, you can see that for this 2 tasks, there's no edges coming to them. So they only have outcoming edges, but they don't have incoming edges, meaning that there's no messages passing to them. So they are initialized with 0, and because they don't receive any messages, they are kept 0 in the output. So basically in practice, you can either add an edge from other nodes to this task, or you can just preserve its previous features by adding the previous feature with their current feature to produce the next one, or just add a self loop so that the task will compute a new task by considering its previous features. And the next will be introduce some learning tasks associated with heterographs. So some of a typical learning tasks for heterogeneous graph include node classification and regression, and link prediction, and also graph level classification and regression. So then we come to the next part, which will basically explain how to solve a multi-robot coordination problem with ScheduleNet. So I'll just go a quick recap of what SketchNet does. So for SketchNet, we extend the simple-time network formulation into heterogeneous graph by introducing robot nodes and location nodes. And we also have this Q-value nodes to let the SketchNet to directly predicting the Q-values of each state action pair for constructing a full schedule for solving a multiple coordination problem. And I have added the link to the full paper if anyone's interested. So basically for the problem statement, I'll give a quick recap for this because it's already introduced in the first session. But basically we will have this, we have two type of decision variables when doing the mathematical formulation of the problem. We have different robots, and apparently each task is only assigned to one robot, and we have the task durations. We have constraints on the task durations for between the start time and end time, finish time of task, and we have the deadline constraints, and we also have the weight constraints. And the following inequalities ensure that the robots can only perform one task at a time. So basically, if the two tasks is assigned to the same robot, they have to be separate on time. So like they cannot overlap on time axis. And we have location constraints, and if the two tasks share the same workstation or the same location, they have also to be separated on time axis. And finally, we have this objective function to minimize, which is usually a mixed span. So basically, usually we'll have this full constraints on the variables, and we can pass them to a MIP solver for solve for optimal solutions, but that's very time consuming when we have a large scale problem like 200 tasks, which we won't be able to find even a feasible solution within like 1 hour or 2 hours. So that's why we want to build a SketchNet to try to learn a efficient scheduler in less computation time, but still give it high quality solutions. Just recap for the MDV formulation. So we decompose the schedule generation process as a Markov decision process, which has a state, action, and transition. And also I just want to highlight about the reward computation. So basically, we designed the reward based on the objective function we're trying to optimize. And because we only know the outcome of the objective function once we have the full schedule, so we designed this specific mechanisms to compute the potential mixed span for a partial schedule and use that to generate intermediate rewards to guide the construction process. And more particularly for the scheduling problem, we provide the scheduling environment implementation following this MDB formulation in this public GitHub repo. So basically, if you go to the repo, it gives you the scheduling environment for multiple connection problem. It also has which is the Jupyter notebook file here you can download. So basically, you need to for this tutorial, we just download the repo to the Google Colab runtime to appear here, MRC scheduling, and we'll add the folders to the system path, and then we'll import the customized modules for the scheduling environment and for the robot team handling the robot team interactions. We'll import this to code. If you're interested, you can open the files to check the exact implementation of that. But for the sake of time, I'll briefly explain each part of this on the high level. So under the data folder, we have provide a simple example problem, which have 17 tasks and 5 robots. So basically, one problem in our case has 4 TXT files. The first one, deadline. This stores the deadline constraints at the as integers, and we have the duration constraints and location constraints and weight constraints. And the following are a visualization of those constraints. So for this case, we see that we are assuming heterogeneous tasks. So basically, in this case, the first task takes different times for different robots to complete, and it has location assigned to it. So in this case, task 1 and task 2 both is located in this great words, which meaning they cannot be assigned execute at the same time because they require the same sort to work with. And those are the weight constraints which specify that the task I has to wait a certain amount of times after task G finishes. And we also have deadlines for this case. And loading the problem to the scheduling environment is straightforward. You just simplify the name to the data, and then just initialize the scheduling environment with the data files. And also initialize the robot teams based on how many robots we have. In this case, we have 5 robots. So, and these are some parameters on the map size, which we're using a 3x3 map. So like the coordinates will be from 1 to 3. And the constraints are stored as NumPy arrays in the environment. So if you call this duration, deadline, weight, and location, you can check the constraints loaded by the environment. And you can print the environment maintain the partial schedule, which was initialized with task 0. So here we use task 0 as a marker for S0, which is the time origin. So basically the task ID starts from 1 to 17. In this case, we have 17 tasks. So task 0 is like reserved for the time origin. So in this case, every partial schedule has a 0 in it because it will start from time origin, and during the process of schedule generation, we gradually add different tasks to it. And the scheduling environment maintains a simple tempo network based on the partial schedules constructed so far. So if you print the graph, it's a simple tempo graph with 36 nodes and 76 edges. So the nodes are S0 and F0, which S0 is the time origin and F0 is the finish marker. And then we have start time and finish time, task 1, task 2, all the way goes to task 17. And in practice, we developed a novel simplification trick to reduce the number of nodes by half. So pre-processing the ST with Johnson's algorithm to find medium distance graph. So basically, the environment maintained a half distance graph, which is a simplified graph that only have half nodes. Like here, we are also presenting the finish node F0, so it's almost half. And those are the nodes will be used. In this case, S will use the start time of task 1 as the task node of task 1. And if you go to if you open the code in the scheduling environment, the core code is the insert robot function. So this function is similar to a step function in OpenGI Gym environment. So if we go to the step function, it will take a task agent pair. So TI is the task number and RJ is the robot number. It will append this task to this robot's partial schedule and update the simultaneous network accordingly. And besides that, it will also compute the reward for this insertion and tell you whether this insertion is a success or a failure, or like whether you have an infeasible schedule encountered or this still feasible, and also a down meaning whether you have finished all the insertions, meaning you have a full schedule. So, like currently we also have ongoing work to convert this scheduling environment into OpenAI Gym compatible ones. And the schedule generation using ScheduleNet is very straightforward using simulations through time. So basically, we cast the schedule generation processing in time-based route fashion to avoid possible delay among different robot schedules. So we start from time origin. At each time step, the project first collects all available robots and it picks a robot from those available robots and tries to assign an unscheduled task using is the queue function, which is represented by ScheduleNet. And it repeats this for each time step until no robots available. Then it steps the next time step and after collecting the robot task paired for the current time step. And this repeats until we either have all the tasks scheduled to one robot or we have an infeasible schedule, meaning we have a failure. So next we'll break down how a single decision step like here works in using ScheduleNet. So first, we need to pick a robot. When generating a schedule decision, we first pick a robot using heuristic functions like the pick robot function. So basically, let's start with 0. Here we start with time origin, so the time point is 0, and we use this function to pick a robot by minimum duration. So this function is in the utilities function here. Basically, this function will pick a robot from the set of currently available robots by some heuristic rows. So here we have developed 3 different rows versions. The first one, we will prioritize the robot with the minimum average duration on unscheduled tasks. The rationale between this is like we treat this average duration as the capacity metrics on each robot's proficiency, and we want to prioritize robot that can finish most of the tasks the fastest. We also have other rules for picking the robot, but for this solving, we can stick to the picking the robot had to test the minimum average computation on all the unscheduled tasks. And in this case, we are picking robot 5 because the robot ID started with 0 in the code, so we shifted by 1 for visualization. And before we picking a task, we need to first collect the valid tasks. So the valid tasks basically are just simply we collect the unscheduled tasks by calling this get unscheduled task. As the scheduling environment maintains the minimum distance graph of a STN, we can filter out the tasks of which the lower bound of task start time is greater than the current time point, which means the task cannot start at current time. And for instance, for this one, we have unscheduled, all tasks are unscheduled, but because we have weight constraints, some tasks cannot start immediately because their precondition are not satisfied. So after filtering based on the STN, we have those tasks as candidates to select by the ScheduleNet. Next, we pick a task using the ScheduleNet. To doing so, we need first to build a heterogeneous graph from the current problem state. So in this case, we import the build graph function from the utils files we provided. So basically, you can check the source code here, but basically what this code does is it takes the half DG graph, which is the simplified STN graph from the environment. It takes some information on number of tasks, number of robots, and other informations on the partial schedules and select the robot. And then it builds the graph by filling the data dictionary, filter dictionary by each hash type, and then call this DGL heterograph function to generate the graph. And because we are dealing with some simultaneous network which are like a weighted graph, so we also need to attach the edge weights to the graph. And as a result, you can run this to build graphs which have 9 locations because we are 3 by 3 and 5 robots and 19 task nodes, and we also have 12 Q value nodes. So basically, we create 1 Q value nodes for each valid task. So basically, we have 12 valid tasks, so we have 12 Q value nodes. And here we just you can print out the visualize the meta graph, which define all the edge types we use for generation. So here you can see that we have this Q value nodes which connect to the robot, the task, and the state, which evaluates assigning this task to this robot in the current state, what the outcome, like the estimated Q value for this. And the thing is, we want to, we have this R in, T in, and S in, and for different type of edge coming in the state to distinguish the in edges with different source type names. The same applies to the two edges. So the robot two value edges, we use R2, and for task two value edges, we use T2. So they have different, so they can be differentiated just by pulling the edge name. So this will give you a simplification when implementing the message passing layer. And also, we have this code to plot the full graph. Because it's a giant graph, so it will take some time. So basically, in this graph, we have this 9 location nodes, and we have 4 robots nodes, and then we have all the task nodes plus the start time and the finish time. And then we have this one state aggregation node that summarizes all the information from every other node and use it for predicting the Q values here. So we have 12 Q value nodes because only 12 tasks are valid to be assigned at the current time because of precondition constraints. And next, we'll provide this head graph node helper to take a problem state and generate the corresponding node features as a dictionary keyed by the node types. So this is similar than our previous example in that it takes those arguments based on the current state from the environment, and it prepared this feature dictionary, and it filled out the task features, location features, robot feature, state features, and value features, and return the dictionary to be used. And you can import it from the utility files. And for this case, we generate the features for this particular state. You can print out dimensions of each type of feature, and also for the state feature. The state feature is a 1/4 tensor, which tells you the total number of tasks and the task assigned so far, which is only just the time horizon, so it's 1. And we have the number of locations and number of robots, which is 5. And the Q value nodes are initialized at zeros because it's just used for predicting the Q values and don't need any input features for that, because we are connected to the state action pairs, which already gives enough information for doing the estimation. And next will be the core part, which is the heterogeneous graph attention layers. So the feature update process in head get layer is conducted in 2 steps: per edge type message passing followed by per node type feature reduction, which means for every type of edge in the graph, you need to specify a message function and a reduced function. So for this case, the full implementation is under the folder graph and head get folder. So for this folder, you have this, I'm posting the code here, which is basically a heterogeneous graph attention layer, which takes a dictionary of input dimensions and a dictionary of output dimensions, and also the type of edges. And those two are, this is the hyperparameters for graph attention mechanisms. And we can specify whether we want to use ReLU for the final output. And the full implementation is huge, so I'll briefly talk about the structure. So first one, you have this initialization part, which initializes the learnable weights for each type of edge. And for each type of edge, you need to define the attention edge type, which computes the attentions for that type of edge, and also the message function and the reduce function. So for example, those 3 functions defines the attention function, message function, and reduce function for the STN edges from the STN. And the next 3 define the task location, the corresponding functions for task location edges. And basically because we are doing, we're also counting the edge feature, so there's no built-in function for this. So we're writing the our user-defined functions for those relationships. But for some of the relationships, here this will be here is the main forward pass, which basically first update the features of each input features and then applies compute the attentions for each type, and then assemble the function, like the function for message passing and reduce function. So here you can see that for those type of edges, we are using our like customized message function and reduce function. And for those edge types, we're using the built-ins because those but simply just copy the feature from the source to destination and sum them up. And we can import the class using this code, and as a result, those are the functions corresponding to the code implementation I showed in the right part. So basically, for the task nodes and robot nodes, we are merging, we are receiving the features and also the edge features when doing the computation. But for other types, we don't have features for the edge. We just compute the message received from neighboring with some attention mechanisms. And for the value nodes, because each value node is only connected to one robot, one task, and one state, so there's no attention mechanism for them. That's why in the forward pass, we can just use some built-in functions to simply copy from source to destination and sum them up. And in practice, to stabilize the learning process, we also utilize the multi-head attention proposed in the original graph attention network paper, and adapting to fit the heterogeneous graphs. In particular, here's the code that implements a multi-heterograph layer based on the head-get layer. So basically, we just need to specify the number of heads we want to use, and it will create a model list that contains different heads, which will be computed in parallel the features and concatenate at the output level. So we use k-independent head-get layers to compute node features in parallel and then merge the result as a multi-headed output with a concatenation operation for each multi-layer in SketchNet. So basically, in the for loop, we just compute for each heads, and then merge the result value by concatenation or average. Because in the last layer, the SketchNet will predict a one-dimensional numeric value for the Q values. So in that case, merging the multi-head result with concatenation is no longer viable for the last layer, as it will give a k-dimensional output. And because we want a one-dimensional output, so we use the averaging, like take the averaging of all the heads to compute the result for the final output. And also, because in this case, we are minimizing the mix span, in which case we are maximizing the negative value of the mix span. So in that case, the Q scores will always be a negative value. That's why we don't use ReLU for the last layer. And you can run this code to build the multi-head attention. And then once you have the basic layers, you just build the SketchNet by stacking several head-get layers in series. It's just simple as you build a normal deep neural network that you have first layer, second layer, third layer, and fourth layer. Each layer is a multi-head heterogeneous graph attention layer. You just need to compute the input dimension, output dimension, and hidden dimensions for the hidden layers, and output for the output dimension, and specify how they merge different heads. And the forward passage is simple. You just pass the output of previous layer to be the input for the next layer, and organize them in series to return the final output. And in this case, when initializing a scatter model, we need to specify whether you want to do a CUDA, whether use CUDA or a CPU. And you need to specify the input dimensions, the hidden dimensions for each type of node and output dimension. And also here is what we return from the meta graph, like the full edge types in the graph. And we're using 8 number of heads, and you just initialize the sketchnet model using this code. For solving this, we need to turn it into evaluation mode. And if you run this code, it will print out the details of each layer. And we can we'll skip that now. So for this tutorial, we have provided a trained checkpoint and shared it in the Google Drive link. So basically, you can copy and paste a shared link from Google Drive and download the checkpoint to the Google Colab workspace through this link. And in this case, this is the checkpoint we provide. And loading the checkpoint, just you specify the name of the checkpoint and load the weights to the checkpoint. One thing to notice that the checkpoint is training with a GPU. So if you want to load it to a CPU-only device, you need to map the location to the CPU. For this case, it will print this all case match successfully, meaning it's converting a GPU model to a CPU model. And the prediction for using scheduling is straightforward. So once you have the network model, you just pass in the heterogeneous bar we built, and also the feature dictionary we prepared, and you run it to get the results. So basically, the result will contain a dictionary of the output, task node feature, location feature, robot feature, and state and value node feature. So because we are doing Q-value prediction, we'll get the value node prediction and print out. So for this example, the predict Q values are the following for each type of value task. So basically, those numbers aligns with this value task. So basically, we can know that the Q values for assigning task 1 will be minus 53, and the Q value for assigning next task will be this one. So in this case, once you have this Q value, you can select the task that has the largest Q value, which you just use a AAMAS to select the best task to assign to robot. So in this case, when you do the AAMAS, the ID is 7, which means the select task is the 7th of the value task, which is task 12. So in this case, we know that using the scheduler, we will assign task 12 to robot 5 as the first scheduled decision. And next we provide a helper function to visualize such output predictions. So this gives a save plot action function, which will save the plot for output. And if you run this, you will get an output of step 1 for the first step. So this figure gives the normalized prediction for the Q values for all the value tasks. And we can see that in this case, the scanner will favor task 12 because it has a much higher normalized Q value predictions. And in that case, we'll assign task 12 to robot 5 and move to the next step. Once you get the task selection with the ScheduleNet, you will assemble a schedule decision, which is a task agent assignment. You will insert first you get the duration for this task on this robot, and then you will perform the insertion to the environment and step forward. And also update the robot teams with the chosen task and the chosen robot and the task duration and the current time point. In this case, for the first step, at time 0, we are picking robot 5 is task 12, and this task takes 7 units of time. And that's done for this decision step. And what we'll do next is we will repeat for the next step. We repeat the whole task robot generation process until a whole schedule is generated or we encounter infeasible schedule. So basically, once you do this, you will turn to this step with pick robot step by running the pick the next robot. In this case, if you run this, the next robot picked is robot 2, like from the available robot. And then after the insertion, you will get a new set of unscheduled tasks and also a new set of valid tasks. So in this case, for the new unscheduled task, because task 12 has been scheduled, so it doesn't appear here. And because based on the insertion of task 12, the STN updates, and there will be some new new constraints we enforce in the STN. And after filtering on the STN, the set of valid tasks reduced, because remember that task 12 has location is in location 2 by 2, which means that for the current time step, location 2 by 2 is occupied by task 12. So any other task that requires location 2 by 2 to work cannot be scheduled. It's became invalid until the task 12 is finished. And at the end, and then we'll do this, do the for loop for the next task agent assignment. And here, next we'll provide a for loop for schedule generation on this example problem. So based for that case, we'll reinitialize the environment to reset to the start state with start decision step 0. We have this parameter terminate parameter to check whether we get a full schedule or we have an infeasible schedule. And I have wrapped this this pick robot process. And basically, we have this helper function for picking a task using the schedule net. This is basically a copy paste of the previous code we provide in this Q value prediction part. And then this will be the full for loop for picking a task. It's except it for the basic logic is same. For each decision step, you pick a robot and you check if there's robot available, you get the tasks that can be assigned, and you build a graph from using this state, and you prepare the features for the graph, and you do this schedule prediction by returning the Q values and choose a task based on the Q values. And based on the choose task, you do the insertion, interact with the environment to insert this task to see if it gives a feasible schedule or unfeasible ones. After that, you will check if the environment terminates based on the schedule, and then you attempt to pick another robot. If there's no available robot for the current time point, you move to the next time point and do the same. And if you execute this point of code, you can see that we are predicting the each steps. So basically, because we have 17 tasks, so we have 17 decision steps. In each step, we pick a robot and we pick a task. And here you can notice that for some step, there's only one task available, and then for that case, we can directly pick that task and simplify the computation. And at last, you will have a feasible solution found for a make span of 35 in this case. And you can and the robot team has a function print schedule to print the whole schedule once you have found one. And you can also access the schedule with the partials from the scheduling environment. So this gives you the schedule of robot 0, which is assigned to task 9, which start from 0 to 2, and task 5 start from 2 to 7, task 3 start from 7 to 15, and task 7 start from 22 because there's some waiting constraints for it. So it starts from 22 to 31. And then at last we have task 4 start from 31 to 35. And after 35, our task has been completed. And we have a feasible schedule. And as mentioned by Professor Gambole, we have a demonstration video available as a supplementary talk for the paper. If you go to the link and scroll down to the bottom, you can find a link to the video demonstration, which print out all the intermediate predictions for each time step, and having the executions for 5 robots on a 3x3 map for completing tasks. And next, we'll go to the final part of this one is to training the SketchNet. Because we have MDP formulation, we can train the SketchNet with reinforcement learning from scratch or imitation learning, or just a blend of both efforts. In this case, we use imitation learning because we already have some expert data set that so basically we can solve the problem optimally using a commercial solver with a small scale problem. And given the scalability of the heterogeneous graph, we expect that exploring such expert data on smaller problem to train the SketchNet can generate well towards solving unseen problems in a large scale, and it saves much time compared to a reinforcement learning baseline. So for that case, we build the transitions as the transitions of a state action next state pair stores the current graph, current partial schedules, and the location constraint, duration constraint, and also the task picked for the current state and the robot picks for the current state, and also the reward for the next state. And those constraints, those loss functions has been explained in the previous section, so I'll go over quickly. And we provide a full training code in the named learning rate scheduler train. So this code will be the training code for training a SketchNet using imitation learning with expert data set on small problems. And the core part for loss computation is here, compute the TD loss for the expert and learn from demonstration loss for alternative loss. So basically the core code I've defined here. So basically, once you have the predictions from SketchNet, you check for the actions. If there's only one actions, you directly train your SketchNet to predict that target value. And if there's multiple actions, you have this offset to ground all the alternative actions was not chosen by the export demonstration here, which will be target list. And then you have, so basically you assign different truth values for the Q values for expert action and Q value for non-expert actions. Once you have this, and then you compute the loss between the predictions and the target values for each Q values, and apply some weights between the expert loss and alternative loss. And okay, and that's it. Due to time limits, we cannot provide a full training because the training will take like 1 or 2 days for our problem. But thanks for presenting. If you have any questions, feel free to put in the chat. So at the end, I include some references for both the papers and also the documentations from DGL on heterogeneous graphs. And I will post this. I post in the website if later you want to visit and walk over the code by yourself. Okay, thanks to everyone. So I will stop the recording now. And if you have any questions, you can type in the chat.